Click show more on the descriptions below if you want to download the code and try the simulation out on your own with processing. Earlier this year, on January, I made a video about a three-dimensional, three-body interacting system. And those three objects interact via gravity. That's the video I made. Now, I thought it would be very fun to make an extended video from that. And so this video is going to be about making not a three-body interaction system, but an n-body interaction system whereby any number of bodies that I want could interact by gravity in a three-dimensional environment. So that's going to be the simulation I'm going to be making today. Now, if you see at the right side of the screen, you can see this equation. Now, this equation, if you go back to the video I made earlier this year on January, you can see where I get this equation from. And for those of you who need some explanation about where this equation comes from, this basically means that the acceleration of object I in the d dimension, and so here d could be anything from x, y, or z. D just indicates the dimension that the object d just indicates any dimension, x, y, or z, and of course we're going to have to use both, like all three of them. But saying that d indicates the dimension and I indicates whatever ith object is experiencing that acceleration, we could make this equation. And here r, p1, pk, so k here means any object from object number 1 to n, and therefore n is our number of objects. So we're adding all the effects of acceleration. Because acceleration is a vector quantity, we could just add all of them. And we're adding all effects of acceleration in the d dimension from object number 1 to object number k, to object number n. And of course, we're not considering itself, so we're saying that I is not equal to k. And then what we do is we have, in the numerator, we multiply the mass of the case object, so this object times di minus dk, which means, for example, when d is the x dimension, we're basically subtracting the x distance between the ith object and the case object. And we're dividing that by the distance from point, so the coordinate of the ith object and the coordinate of the case object, to cubed. And so this is going to be the equation I'm going to be using to make the n-body simulation. Now let's go on to coding. Now, first of all, we're going to need mass, and in this simulation, I'm just going to give all masses the same value. So all masses are going to have a mass, for now, let's say 10. And then I'm going to also have to indicate the number of objects I have. So int num is going to be the number of objects we have in the simulation. And keep in mind that in the three-dimensional environment, I'm going to make a cube, and then I'm going to arrange the objects in the form of a cube. And so for the number of objects I have, I'm going to have to have a cube number. And so for now, I'm just going to say 1000 because that's 10 cubed, so that's a good cube number. And then I'm going to need the size of the ball. Now the size of the ball, ball size, is going to be important because when we have three dimensions, we're going to need some way to indicate the z dimension. We have just a two-dimensional screen, so we don't have any way to indicate where the object is in the z dimension. And so I'm going to indicate that by the ball size. So when the ball has greater z dimension, thereby the ball is closer to the screen, it's going to have a greater, it's going to appear larger in the screen. And that way we could indicate, the z dimension by visual terms. We're also going to need the timestamp. Every simulation has a timestamp, and timestamp is the smaller the better. But for now, I'm just going to say like 0.05 seconds. And these values I could just change it when the simulation goes wrong or the simulation doesn't seem fluid. And so yeah, these are just temporary values for now, and I could change it up. I could change it when it doesn't seem right. Now what I'm going to need is I'm going to need a lot of lists, so array lists. I'm going to have to define a lot of array lists that contain the same form of variables. And basically what I'm going to need is position array list. I'm going to also need velocity array list and acceleration array list, all x, y, and z. So I'm going to need 3 here, 3 for position, 3 for velocity, and 3 for acceleration. So I'm going to need a total of 9 array lists. So defining the array lists are all going to have a float values, a specific float value, not an integer, because we're going to have to do all kinds of complicated calculations, and they're always going to be decimal values. So I'm going to define float lists. So float px, which is our x position, is going to be new float, and there's going to be numbers of values in that list. And so I'm just for now I'm just going to say that, and I'm going to have to do that 9 times because I have 9 lists. 4, 5, 6, 7, 8, 9, and this here is of course going to be position y, position z, and here velocity x, velocity y, velocity z, and acceleration x, acceleration y, and acceleration z. Now here, because I have 1000 as my number of objects, each of these 9 lists are going to have 1000 values, each indicating the informations about each object in the simulation. And now I'm also going to need another one for position, because I might be able to, I might not, but I may also want to draw a line, a trajectory line that indicates the line that the ball is moving in. And to do that, I need to have the previous position. I have to take record of the previous position of each object, so that I'm able to draw a continuous line that the ball, that traces the position of the ball, the objects. Now I'm gonna do my graphics. So pgraphics canvas, void setup. And now what I'm going to do here is, first of all, I can't just give random positions to these objects, because that's going to create a bunch of mess. What I'm going to do is I'm going to arrange these 1000 objects in a cube, as I said before. So that's why I set this as a cube number. 10 to the 10 cubed is 1000. And so I'm going to have to make a cube-shaped arrangement of these 1000 objects. So to do that, first of all, I'm going to make a for loop from 0. So I'm going to loop this for loop. I'm going to loop it num times, so 1000 times, and say, well, when you imagine it, well, first of all, the distance between each objects are going to be 100 in each dimension. So the coordinates, if you imagine, would be 0, 100, 200 to all the way to 900, and then I'm going to subtract 450 from all values, so that I get a evenly arranged position, if you get what I mean. So minus 450 to 450, and each being spaced 100 is my goal. And to do that, I'm going to first of all say, well, the ice value of px is going to be this. First of all, it has to contain all objects. So it's gonna what's gonna happen is a pattern is gonna be repeated from 0 to 900, then again 0 to 900, then again 0 to 900. So all I have to do is get the remainder of I by 10 and then multiply that by 100, and that's going to give me a repeating pattern of 0 to 900. But now 10 here is 1000 cubed. I can't just say 10 because I'm defining num, and so I'm going to have to make this program universal. I can't just say 10. I have to say 1000, so num to the power of 0.1 over 3. 1000 cube, 1000's cube root is going to be 1000 to the power of 1 over 3. And so I'm going to do that. The remainder of I from the power of num, comma, 1 over 3, so 1 over 3, 1.0 over 3.0, and all of that times 100 is going to be my value. But as I said before, I'm going to have to then subtract all values by 450, or you could say I'm going to have to subtract all values by 100 times 9 divided by 2. Yeah, it's always going to be 100 times num to the power of 1 over 3 minus 1 divided by 2. That's going to be the way we get the evenly arranged objects. So I'm going to have minus 100 times the power of num and 1.0 divided by 3.0, so that's going to be give me 10, and I'm going to have to get 9, so get minus 1, and by this way I'm going to get a value of 450. And for example, when I have 8 objects, yeah, you get what I mean, right? So we're subtracting. So the original list here contains values from 0 to 900, and to even that out, we subtract 450 from all values to get an evenly shaped, or not an evenly shaped, but an evenly a cube that is symmetrical to all the axes. Yeah, that's what I mean. A cube that is symmetrical to all of the axes. And I do the same thing for py, but py is going to be slightly different because now if px contains all values repeating from 0 to 900, then 0 to 900, py is going to must have a value that is periodical by every 100 every 100 iteration it's going to repeat, because when you imagine a cube with 1,000 balls, the lowest 100 are going to have the same y dimension, the same y coordinates, and then the second, let's say the second level is also going to have now going to have a different y value, and then the third floor, the fourth floor, and so on. Imagine the y coordinate as a floor. And so what I'm going to do now is say this is going to be then I to the remainder of 100 now, not 10, but 100, and then multiply that by 1000. So the remainder when I get 100. So zeros to 99s, they are assigned a value of 0, and 100s to 199s get a value of 100. and the 200s to 299s get a value of 200, and 300s to 399s will get a value of 300. And so what I'm going to have to do here is say, I'm going to have to first of all subtract I minus the I, subtract the I percentage of, so I, the remainder when I divide I by 100, so power of num, comma, 2.0 divided by 3.0, because that's going to give me 100. That's going to be the universal meaning of 100, so num to the power of 2 over 3. And that's going to give me, for example, in here, when I do that, that's going to give me, so in this example, that's going to give me 200. So here, that's going to give me 200. And then, because that's 200, I can't just use that value right away because I'm using a specific example of 1000. What I'm going to have to do is then divide that by, so that all of that here, divide all of that by now, divide that by 100. So the universal meaning of 100, which is power of num, comma 2.0 divided by 3.0. And then that will give me either 0 here, 1, 2, 3. And then what I do is multiply all that by 100, and that's going to give me the universal coordinates that I need. And then I do pz of I. Now pz of I have to contain values that are, let's say pz, that's going to need, in the z dimension, we're going to have in the z dimension, we're going to have the zeroth object to the 10th object are going to have 0. And then the 11th object to 20th object, 9th object, and then 10th object to 19th object is going to have 100. And then 20th object to 29th object is going to have 200, and so on until we have 100th object to 109th object. Now when it goes there, it's going to go back to 0. So here, let's say 90th object to 99th object is going to be it's going to be 900, and then and also I forgot to subtract this here always to here too. So now pz, I'm going to need this pattern, and so to make this pattern, I say, well, first of all, I must have to subtract the remainder when I divide by 10, and then divide by 10 of that value, then multiply 100. Is that what I have to do? So divide by 10, remainder when I divide by 10, divide by 10, Okay, first of all, I say I minus I percentage of power of num, comma 1.0 divided by 3.0. So that's going to be 1 I minus I remainder of I divided by 10. So in this case, for example, I'm going to have a 90. Then if I have a 90, I divide that by the power of num 1.0 divided by 3.0. Wait, what? Yeah. And then now I'm gonna have now it's gonna work from the 0th object to the 99th object, but from this object I'm gonna have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then here it's gonna be 10, and I don't want that, so I'm gonna have to wait, get the remainder of that, all of that by 10 again, because that will give me will that give me, yeah, remainder of that by 10 again, and then I could multiply 100. So that by 10, so 10 being num, comma 1.0 divided by 3.0. And then what I could do is, now I multiply all of that by 100, and that's hopefully going to give me the right values. Now, because I'm not sure yet, what I'm going to do is I'm going to print px first. Now, if I print px, let's see what happens. And what? Should this be? Okay. That seems like it's working, but that's very confusing. Did it work? Wait, it's lagging. Wait. Well, first of all, I'm going to have to divide this here by 2.0. As I said before, 900 to 450. I'm subtracting 450 from all values. Like in the case of 1,000 numbers, 1,000 objects, and then do that the same here, and also minus all that, and pz as well. Now hopefully when I run this, And after the for loop, I print pz. Hopefully I'm gonna get a list that contains the right value. So let's see from the middle. So wait, what? Is it not showing me the first one? Well, let's see. So let's see from, so the pattern in px was that it's simple, 0, 100, 200, 300, 400, all the way to, well, minus 450 to 450, and then all the way back to minus 450 to 450. That's the pattern we have for the x dimension. And here, as you can see, we have minus 250 all the way to 50, 450, 550, wait, 550? There shouldn't be a 550 because it should stop at 450. Wait, 0, because here it's going to be, what has to happen is, maybe it's 10, 100 times 9 minus 450. Divide by 10, so percentage of number by 10. Maybe it's because there's a like a float value here somewhere. But I think we could, yeah, I think this works because 550 and then back to 350. As long as there's a repeating pattern every 900, it's fine. But I think it is working. So I think that's fine. Px is fine. Now when we look at py, a similar thing should happen, but we're going to have a slightly different pattern. So it's repeating every, so for 100 values it's same. And then the next 100 values it's also going to be same. So for 100 values it's same, yeah. And then from 600 it's going to, yeah, from 600 1 doesn't really matter. It's now have changed. So 150 now, 250, all the way to 450. So that's working good. That's fine. And then we have pz. Now pz, we're going to have a pattern that's, so 0, 100. So every 10 values it must change, but then every 100 value it must go back to 0. So from here we see that, okay, every 10 it has changed. 10 changing, and when we get to our maximum value, 450 or 550 in this case, we go back to minus 350. So that's working good. So we're done with. So when we here, let me just get the pattern right. So let's just write the pattern. So that's 0, then 10s to 19s, 100, then 20s to 29s. We have 200. Wait. No. We have 0s, 10s, 20s are all 0. Then we have 1s, 11s, well, first, and 21st. We have 100, and we have second, 22nd, 11th, 21st, and 22nd. We have 200, and so on. So that's the pattern, and it seems like we have got our pattern right, so let's move on. Now after we defined all of these position vectors, we now define the velocity vectors. And the velocity vector for the x dimension. So all of these velocities, I'm going to give random values, slight random values, so that when I start the simulation, it's not going to be like a regular stance. It's gonna need some kind of random shift so that the pattern that's created by the simulation, like the simulation doesn't create a pattern, it creates, like, what would happen to all these masses when they're all, intertwined with each other by the effect of gravity. I don't want to see a pattern. What I want to see is what would happen if all of these dust particles or all of these masses are together by the effect of gravity. So I'm going to give slight random values. So let's say random, and then what I want is like something like from -1000 to 1000. So let's say -1000 to 1000. But because I want a float value, I'm going to add 2 more zeros and then divide that by 100 so that I get a float value. And so that here, and do the same for Vy and Vz. And so now this will create some random movements in the initial state of the simulation so that I don't get a pattern, but rather I get an actual simulation. Now, then because for PPX, so acceleration I'm going to do it later because that involves calculation. But PPX, I could say PPX is basically equal to PX, PPY is equal to PY. At the start of the simulation, there's like no previous value, so the previous value is equal to the after value, and so PPX, PPY, and PPZ is equal to PZ. And then that's the end of our that's going to be the end of our for loop. Yep. And then I just basically give the size of the simulation. So the size of the window I'm going to be using. So width here is going to be like 1,500, and then for the height I'm going to use, for now I'm just going to say like 800, like 750. That will work. 700. Let's say 800. Size 8. 1,500 by 800, frame rate like 60, the canvas equals create graphics, same size, and then we begin draw. Now the background, I'm gonna use a black background because I wanna create the sense that it's space, and I'm gonna have to see and draw. And yeah, and also to be sure, let's just print our let's let the program print all the position vectors. Right, so that's done. Now I move on to drawing. So void draw. Now here, this is where we actually do the simulation. Now, first of all, I create the image, so canvas 0, 0, stroke 0, stroke weight is also going to be 0 because I don't want the objects to have any kind of indication of, let's say, outer edge. I just want that to have transparent outer edges. And so stroke weight is going to be 0, and let's translate all of the points to the center. So it starts here, so I'm going to translate it to half of these values. So 750, 400. That's going to be, yep. And then for integer, because we already used j, like, it doesn't really matter. So, but like to be sure, just use j in this loop. So from j is 0 to all the way to num. We're gonna have this here is basically, this is like drawing our shape. So every time the code runs, there's going to be a different ball size. And the ball size is going to be so for every object, it's going to have different ball size depending on the z coordinate. and so the z position. And so the base size of 5, I'm going to say the bigger the z value, the larger the size of the ball. And so divide this by 100 or something. Like these values, I'm going to change it like after I run the simulation if it looks like if it doesn't look good. But for now, let's just say it like that so that the ball gets bigger when the z position gets larger. And then we fill the ball with yellow. Let's say yellow. So yellow is RGB. So FF00, red and green. Yeah, red and green. And then we draw our ellipse or our circle. Because there's no circle, I'm going to need to say ellipse. And so now here, what I'm going to do is, let's say, well, first of all, the z coordinate is going to be, well, px, of course. And then, but, well, the x coordinate is going to be px. But then, we're also considering the movement in the z coordinate would also correspond to an x coordinate in the screen. So even though the z coordinate and x coordinate are different in our screen, a movement in z coordinate will both affect both the x coordinate and the y coordinate as you see on the screen. And so we say pxj minus pz of j divided by square root of 2.0. And then we have for the y, in processing, we know that the y coordinate, when we have a positive y, it goes down. So we're going to have minus py of j plus pz of j divided by square root of 2.0, comma, ball size and ball size for our radius. And here, because I think like our values are too big, I'm just gonna say like divide all of these values by like 20, so that our simulation is not like all the way. So like these values, I'm gonna change them again if the simulation doesn't seem right. But for now, let's say divide all of these values by 20, so that the simulation is like confined to the center point, not being like everywhere around the screen. Now what we should do is now it's the end of this for loop, and then we make another for loop that finally calculates our acceleration using this equation. So for int we use j, so let's use k larger than none, and k plus plus. Now in this loop, first of all we set all of our acceleration coordinates to acceleration quantities to 0, because we're just starting the loop and we don't want any other thing to, like, we don't want previous values affecting our new values. So all of these accelerations are set to 0, and then we have another for loop. So let's use L. And this is basically comparing our, so k here is the object that is accelerating, and L here is the values that we use to calculate our acceleration effects of all these different objects. So when you see, so in this equation, I here is going to be our k, and k here is going to be our L, and n is going to be our null. So it's kind of confusing, but keep in mind that k is I, and L here is k. Okay, it is quite confusing, I know, but let's just go. And so first of all, we have to make sure that these two objects are not the same object. So only if k is not L do we run this code. So k shouldn't be L. And then if k is not 0, if k is not L, then we say, well, ax of k here is equal to, when we look at this equation, we have, well, g, and I don't really care about g because g is just a constant, so let's just not use g. When we do use g, then the simulation is going to be really, really slow, because g, like, it's using real life values, and here our mass is only 10 kilograms. So imagine like we're doing all of this the same, but like the charges or the masses are like enlarged into really large amounts. So let's just not care about g now and say what the acceleration is. So basically we're gonna have to add all of these values. So we start at 0 and we don't add, like we don't say ax of k is equal to this new value, one value, because we're not only using one value, we're using a sum of all of these values that we get from this loop. So what we do is we do plus equals. So we're adding on to the acceleration by running all of this like for loop over and over again to compare k with all values of L, like the specific value of k to all values of L from 0 to none. So ax of k plus equals minus, when we look at this equation, minus mass times dimension. So we're in the x dimension, so we have px of k, it's going to be px of k minus px of L. Yep. And then what we do is we divide that by something, and let's say here, let's say it's length or distance cubed. Now we don't have anything with distance now, so we're gonna have to say float distance equals 0. So we define our distance in the for loop, and then in the if statement, here is where we define our distance. So distance is equal to the square root of something squared plus something squared powered. So power plus power plus power, and we know that's by 2. And when we calculate the distance between two objects in 3 dimensions, what we do is subtract the x coordinates, y coordinates, and z coordinates, and then we raise them, all of them, by power of 2, and then we square root. So this is basically the function for calculating our distance. So it's should I define my distance, like, does this work? Float distance equals 0. Wait, I think I have to define it like before. So let's define my thing here. So float distance is 0. Now we can use our distance. Oh, I guess it should be inside. Yeah, distance is 0. And then power of, yeah. So it's going to be px of k minus px of L. Yep. And then here it's py of k minus py of L. And here it's pz of k minus pz of L. Alright, that's good. And now when we do distance to the power of 3, or that doesn't work, say power of distance comma 3. Yeah, that works. Okay, so now we're done, and what we have to do is just do all of the same thing, acceleration for y and acceleration for z. So acceleration for y and acceleration for z, and they're all equal to that, except we use y, and z. And now that's the end of this for loop. So that ends here, and finally we have a last for loop that basically does Euler integration or Euler approximation of the position and the velocity all accumulated from the acceleration. So what we do is from n is 0 to num plus plus, we say the velocity in the x direction is added to our t. So t is our time interval or time. Yeah, it's our time interval. So it's we add our time interval, our short time interval times our acceleration to the velocity, and that is basically what we do in Euler integration. We add plus equals. We add our acceleration times our time to the velocity, and do the same thing for y and z as well. So y and z. And then what we do is we do all the same thing, but we do it for, so Vx, Vy, Vz, and then position is also now affected by our velocity. So just as we did for velocity and acceleration, we do the same thing for position and velocity to get Px, Pyz, Pz is equal to t times Vx, Vy, and Vz. Now we're pretty much done. All we have to do now is canvas.begin draw, canvas.translate to, our size was 750 or 1500. Is it 1,500? Yeah, 1,500 to 800. So 750 to 400 translate, and then canvas dot stroke weight is 2, and this is basically this is tracing the paths that each of our objects make. So for int and for all objects, we draw a line that goes from previous px to and previous py, and yeah, we always consider, so minus ppz of n divided by square root of 2.0, and that plus previous z coordinate divided by square root of 2.0, comma px of n minus pz of n divided by square root of 2.0, comma p minus py of n plus pz of n divided by square root of 2.0. Now hopefully, if I do that, and also here I'm also going to have to say that stroke weight should, I think should be inside here. So stroke weight, it depends on our z quantity, so 2 plus, or 1 plus 2 plus pz of n divided by, say, 1000. That's going to be, now let's do this for now and see what happens. And like for last, we say previous px, the list of previous x coordinates is equal to px. After we do that, it's important that this is after this, and then previous py is py, previous pz is pz, and finally we end our draw. And hopefully when I run this, so let's save this as, let's say, n body gravitational effect simulation interaction, n body gravity interaction simulation. Yep. Let's run that and see what happens in our canvas. No, the sketch name cannot be identified. What does that mean? Okay. Oh, what? What's up? Oh, I think there's something wrong with the yeah, there is something wrong with the stroke wave, right? Yeah. Let's just not do this for now. Let's just like, I think this is important. So yeah, let's just not like do this for now and just run our code without the lines. But, oh yeah, I think it is working. Is it working? Or is it just getting bigger? Right? Hmm. Nope. Like I think like first of all it's too big. Or so let's say do that. Then run. I don't know. Why are they like separating like themselves from each other? Like, wait, let's like get the time stamp really short to see what really happens. So are they just distancing themselves? Like, why is it? Hmm. Like, there must be something wrong with. Hmm. Why are they just separating themselves? Like, hmm. Wait. I think the problem is. So let's like see this from a really large scale, and then say like that's. I think that would, if I do that, hopefully. Still the balls are too big. Right? Let's use like a smaller number of balls. So let's have like 125 and then see what happens. They're like too far. Okay. So I think the problem is the acceleration is too big. So if I say like I multiply 0.1 to the acceleration value, then I'll get something better, maybe. Was it still too big? Or is it like the problem of minus? I don't think so. Yeah, it's still still doing that. Oh no. The mass is smaller, maybe. Why are they distancing themselves? Or maybe the velocity is too big. Maybe that's the problem. Like they're still like separating themselves. They're not pulling each other. Yeah, I'll come back after like I solve this problem, but like, is it working? Yeah, I'll come back after I solve this problem. I think the problem was that like giving the random velocities here, I think that was a bad idea. So I didn't do that. And when I don't do that, you can see that the 125 objects, they slowly come together and then they just go out in their directions. But as you can see, like in the small like details, they are interacting with each other. But because like the forces of gravity become exponentially smaller, like it depends on the cube of the distance, they just separate each other. I think that that's inevitable. So when I use like 1000 here, it's gonna be better. So yeah, it starts as a cube, and then they slowly they like move towards each other. Yeah, and then hopefully they like explode. Then yeah, and that happens. Yeah, so that's it. It's very interesting. Like, uh, yeah, if you like the video, please click the like button and subscribe. And for more videos like this, yeah, please, you know, turn on your notifications so that you're notified when you want to watch more videos like this. Thank you and see you on the next video.